Greetings, everyone. I want to go over the homeworks from, I said 5.4. This is 4.4, obviously, right? That was a typo. And the first one was number 39, number 39. And so let me write down what 39b is, because that's somehow the real question. And that is, what is 5 to the power 2003 mod, well, actually it's this mod 1001. Now, we have seen the modular exponentiation. It was a quiz on that. And then, so one solution was, but it's not the solution we can follow, but I just want to review you. So one method, so method 1 if you want, but it's not the method we're going to use now, is you have to write 2003 in binary, and then start calculating 5 squared, 5 to the 4th, 5 to the 8th, etc. Remember? And then whatever, and then using these powers, you use the ones that occur in the binary and put them together, all this modulo 1000. So all this is mod 1001. Now, then in the lecture we saw that there is a faster way if you work with a prime. So if P is a prime, so I remind you also what Fermat's little theorem, I'll just call it Fermat, says. If P is a prime, then A to the P is equivalent to, A to the P minus 1, is equivalent to 1 mod P. And A can be any number here, of course, other than 0. So the GCD of A and P is 1. That makes it non-zero mod P. Okay, that's what that is do is that it allows you to reduce this power that you normally have modulo P minus 1. You're gonna then modulo P minus 1. But the problem in this, why are we not using this now? Why is this a much more complicated problem? Is because, so note, 1001 is not a prime, and in fact it is 7, what is it here? 7 times 11 times 13. So it's definitely not a prime, so Fermat does not apply. But so now we're going to look at the second method, that is what A is. So method 2, to nonetheless use this. And what you're going to do is two things. So step 1 is, that is A. So I'll write it, the A step, what you do in A, you calculate 5 to the 2003 mod any of these primes P that we have here. So the primes are these guys, okay? And then you use the Chinese remainder theorem. So these are the P, right? So 7, 11, and 13, I mean. Chinese remainder theorem to find answer. Let's see how it works, how it plays out. So in A, so what are we doing? So there's 3 primes. If P is 7, so what is then 5 2003 mod 7? So now let's review again, how do we use this if P is a prime? Now we're going to use Fermat's theorem, and it is perhaps a little bit confusing. So step 1 is look at P minus 1, that is 6. And take the exponent, so the exponent here is 2003, and you're now going to calculate 2003 mod this 6, not mod 7, but mod 6. Okay? Now, okay, that takes a little bit of work, not that much, of course, so let's do this quickly. 2003 divided by 6, that is 333. So 333 times 6 is 1998. So this happens to be 5 mod 6. There are not many possibilities, so it's not so hard to check this. Okay, I just calculated it. Okay, so that is, now we're doing this. So what does this now mean? This means that, so we, sorry, okay, right. I'm sorry, it's true what I said, but it's not, it's more valuable I want to show you how it works. So let me do so the exponent is 2003. Let's do the long division on it. So it's what I did, but I didn't write it down. It's 333 times 6 plus 5. So what does this now mean? Let's look at this. This guy, okay? That we can break that down in 5333, times 6 plus 5. Right. I'm just going to do the argument one more time because I've done this in the lecture, but so that you see how it works. Then if you have a sum of powers that results in a product of powers, right? That's something that we have been doing many times. So this is on mod 7 or whatever prime that we're working with. But then here is the clue: 5 to the power 6 to the power 333. A power of a power is multiplying the powers, and I keep the 6 inside because what? Because Fermat's theorem for p equals 7 says that a to the power 6 is equivalent to 1 mod p for any a, well, except for 7, but so in particular for 5. So 5 to the power 6 is equivalent to 1 mod 7. This is a special case. Oh, sorry, I wrote p here, but I meant 7, right? So this is a special case. So this whole thing here inside is 1, and now I raise it to the 333 power. It doesn't matter what power it is, it's still 1. So this whole thing is 1, and so we have only this one to calculate. 5 to the power 5 mod 7. And now we can use our other method, which is now much shorter because we're dealing with much smaller exponents. Sometimes, well, 5 to the 5, I think the calculator actually lets you do this, but so you can calculate it right away. But let's just show you how it works. It's good to practice all these methods, because remember, we do all this for very small values just that we can practice this. But these things are really used in cryptography, in coding, and where they're used there with much bigger numbers, where these things cannot be calculated. We need to follow the strategies of calculation that we have discussed. So what we do in this method, remember, we take the exponent. But now there's not 2003 anymore. So this, okay, so let me, sorry, I didn't write it up. So we have reduced the whole thing to calculating this. Okay? I'm going to show two ways of doing this. So the first method is this way. So, okay, we take that exponent. So this exponent, not this 5, but this 5. There are different 5s. Well, and we'll write it as in binary, in powers of 2, 4 and 1. So we have 5. Then we have 5 squared, that is 25. That's 5 to the power 1, right? 25 mod 7, that is 4 mod 7, right? Because 21 plus 4. Now we square again. If we square that, we get 5 to the 4th. If we square 4, we get 16, which is 2 mod 7. Okay? So we have found, and this of course is just 5 mod 7. And what we have is we have 4 and 1, so it's only these two that we're going to combine. And so we see that this is going to be this 5. Oh, what is this here? Sorry. I don't know. Okay. 5. So remember, this is now, we write this, we split it this way, and then we say this is 5 to the 4 times 5 to the 1 mod 7. Okay, I'm writing it all out. Of course, you don't need to write all these things out once you know how the method works, and on the next examples I go for quicker. So what we have now, 5 to the 4th, that is 2. 5 is just 5, so this is 10 mod 7, which is just 3. Okay. Now there is another way that I have already mentioned in another video. So that is, sometimes if your number that you're dealing with is very close to your modulus, in this case 5, now I'm talking about the bottom number, I can replace, be careful, right? I cannot replace the exponents. that's not, but I can replace this 5 with anything that is equivalent mod 7. So I could subtract 7 from it. So I can use that 5 is the same as minus 2 mod 7. Remember, subtracting or adding 7 doesn't change its remainder mod 7. And then we get, this becomes, so this is one way, so second way, well, if you want already, perhaps a third way, this becomes minus 2 to the power 5 mod 7. But what is that? That is minus 32. It's a small number I can calculate in mod 7. Now, the only problem is that it's negative, so I have to add another several times multiples of 7 until it's positive. And this would be, I add 35 to it. So this is a multiple of 7, right? I can any multiple of 7, so this is, of course, 3. And that's, again, what we found. Okay, so conclusion, we know that this is 3. Let's do this now for the 2 other primes. But as I said, I'm going to go now much quicker. Okay. Okay, so now P is, what was the next one? 11. So 2003 mod 11. Okay, so now P is 11, so let me erase this part here. P is 11. So what I do, so the next step here is, I'm going to take P minus 1 is 10. So I will take my exponent, 2003, and write it divided by 10, that is 200 times 10 plus 3. And then I know that 5 to the power 10 is equivalent to 1 mod 11. This is a special case of Fermat's little theorem for A equals 5. Therefore, this whole part in part of the exponent will give me 1, and so I know that this is equivalent to 5 to the power 3 mod 11. So if I worked it out last time. If you don't understand it, work it out one more time. But so as a rule, it says you take your exponent, you take its remainder modulo p minus 1, this is 3, and that becomes a new exponent. Okay. Now, this is such a small number that I'm not going to bother calculating it. That's 125 mod 11, 125. And what is 125? Well, that is, okay, why am I blinking? Ah, yeah, 121 is 11 square plus 11 times 11 plus 4. So this is equivalent to 4 mod 11. So the answer is 4 here. And then the last prime, so I can do it again. So what is the prime now? P is 17, or 13. So 5, 2003. Oh, that's 1 0 to money. Mod 13. So what I do, I take 2003, so P minus 1 is 12. I'm going to do this mod 12. So this is what I'm calculating now. This mod 12. No. Okay, so I don't see it immediately, so I just calculate 2003 divided by 12. That is, so this is 166 times 12, and 166 times 12 is 1992. So what I'm missing is 8 plus 3, 11. So this is 11, right? Sorry, it's a little bit late, as you can see, so I just don't make a silly mistake, so I'm just, right, 11. Okay, so the answer here is 11. No, what am I saying? Professor, what are you doing, Professor? This is step 1. Step 2 is now, this becomes the new exponent. Okay, 11 is the new exponent, so it's 5 to the power 11 mod, mod 12? No, now we're going back to mod 13. So that's the weird thing, right? We switch to 12 and then we go back to 13. It's very confusing. You have to keep your head straight here. So this is again a series power, 11, well, series. It is 8 plus 2 plus 1. Okay, so we have 5, that's 1. 5 squared, that is 25, which is the same modulo 13 as 12. Modulo 13, right? Right? So what is 5 to the 4th? So again, here what I could do, although 12 is much more useful, we normally use, but let me show you what I'm going to do it one more step. You don't have to, and then it will be not much more difficult. So we have 12, but I'm going to subtract 13 from it, and so this is also the same as minus 1 mod, where am I, 13, right? But minus 1 is so simple. Minus 1 squared, that is just 1 mod 13. And what is then 5 to the 8? Well, that is 1 mod 13, because I'm squaring 1. So sometimes it's beneficial to always try to get smaller numbers, because they're easier to work with, right? Okay. So what does this now mean? So result, that is, no. Professor, you want to be too quick. Now, this is what I need. So 511 is, so let me mark the ones I need, 1, 2, and 8. So this will be 5, of course. The 1 gives 5. The 2 gives minus 1. Okay, let's leave minus 1, and the 1 gives 1. So this, we have to calculate is mod 13. Well, if you want mod 13. So this is minus 5. That is minus 5. That is just minus 5, right? And how do you get minus 5? Well, you add 13 and you see that's the same as 8. So the answer is 8. Okay, so this is the first part. This is A. Now B says use this remainder, the Chinese remainder theorem. Because we know that, what do we know? We know that this number, let me erase what else that I don't need anymore, that I can better explain. I also don't need this Fermat theorem anymore, so I'm going to also erase this part here. Okay. I know, and what I'm looking for is this number. Okay. And I know that it is equivalent to 3 mod 7. It's equivalent to 4 mod 11 and equivalent to 8 mod 13. So if I solve this system, so in replacing, I'm going to erase things. So in replacing this is a number it's 3 times the same number. Well, it's a number x that satisfies this, and that. So how do I find x? Well, I use the remainder theorem. Okay, let's do that. So what are our moduli here? Well, 7, 11, and 13. That's the M1. So this is M1. Sometimes people write P1 here. Let me write P1. No, I'm not going to write P1. Let me write M1. Let me write M. Okay, let me write M1. I'll keep M1. And this is M2, and this is M3. What else do we need? We need M, the product of these things, but that we know already. That's 1000 to 1. That's exactly what we want, right? We know that this system of equations, there's a unique solution that is equivalent to x mod 1001. This is the value that we want to calculate the solution, and then we take that value. Okay, well, perhaps to be correct, like both things. Okay, so what else do we need? We need, let me write M here. Okay, and then we need the capital M's, right? What is capital M? It's the product of the remaining 2 primes, that is 1, 4, 3. M2, that is 7 times 13, that is 91. Yeah, and M3 is 77. And then finally, and that's where the work actually really goes, we have to calculate YE ME equivalent to 1 mod little mi. That's the thing that we have to solve. So if I is 1, then we have, so I is 1, this would become the equation Y1 143 is equivalent to 1 mod 7. Okay, now mod 7, that's really, there's only, we're talking here about what, 0, 1, 2, 3, 4, 5, 6. We know already 0 is never an inverse, so it's going to be very quickly. So, but of course, first, what is 144, right? Well, 144 is the same as 140 plus 3, so this is the same as 3. So this is equivalent to 3 times y1 mod 7. And so 2 times 3 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 4, 3 times 5 is 15. That is equivalent to 1. So I just by enumeration, so by trial and error, I find that inverse is 5, because 3 times 5 is 15, which is equivalent to 1 mod 7. So my y1 is 5. Okay, that's, so you see, because our moduli are rather small, this is very quickly done. I is 2, so now we have I2 times M2, which is 91, and all this has to be calculated modulo, and this has to be equal to 1, right? Modulo, what is it? 11. So 91 is 88 plus 3, so it's again 3, so 1 is equivalent to 3 times y2 mod 11. Okay, you see 91. Right? 91 is 8 times 11 plus 3, right? That's where this comes from, okay? Fine, so what now? Again, let's just try. 3 times 2, no, 3 times 3, no, 3 times 3, 12. Oh, 3 times 12 is equivalent to 1 mod 4, so I see 4 is an inverse. So just by trial and error. Of course you can do the Euclidean division algorithm and work it that way out, but for such small number it will not be much work either. But such small numbers you just try. So 4 is the inverse, so y2 is 4. And then finally, but on the test you'll see, I'll throw in a bigger number. Right, I cannot make it too easy for you guys. Okay, I is 3. So now we have 1 is equivalent to y3 times m3, which is 77, and this has to be done mod 13. Mod 13, okay, since it's so late, I'm not going to rack my brain with that. I'm just going to calculate it. If I can get my calculator to come up. Come on, calculator. Okay, sorry. 77 divided by 13, it's 5. And what is the remainder then? So 13 times 5 is 65, so 12. Oh, so 1 is equivalent to 12 times y3 mod 13. Yes. Sorry, my y3, I'm getting a little bit. So what's the inverse of that? Well, again, 12 is the same as minus 1, not 13, right? Again, 12 is so close by 13, I'd rather work with the smaller number. And what's the inverse of minus 1? What number multiplied with minus 1 gives me 1? Well, minus 1. So I see that the inverse is going to be minus 1, but this is of course equivalent again to 12 mod 13. So 12 is its own inverse. Strange, right? That we have a number that is its own inverse, but these things do happen in this modular arithmetic. Okay, so y3 is 12, and then the final calculation. Let me do this here. Now all this can go on. What we have to now do is multiply. So these are the here are the A's. This is the A's, right? These are the M's, and these are the Y's, and we have to multiply all these and add them up. So we have 3 times 143 times 5 plus 4 times 91 times 4 plus 8 times 77 times 12, and this we have to calculate modulo 1001. But notice these are much smaller numbers than 5 to the power 2003. And also 2003 in binary is, well, we're talking here about 2K. This is going to be 11 digits, or 10 or 11 digits. You're going to be kind of busy with this thing if you want to do it method 1 here. So this method is, although it's not quick, it's quicker. Okay, we have to calculate this number, which I'm just going to do. 15 times 143 plus 16 times 91 plus 8 times 12 times 77. It's this is supposed to be 7,392, and then mod 1011. So what is that divided by 1001? That's probably what did I do wrong? I don't know. This that is 7 times 110. This is 7,007, right? Plus what? So this is 707. So what this remains is 385, and 385. Give me a sec. I thought. Give me a sec, guys. I just want to make sure that I got the right answer. I did calculate it somewhere. Double checking. I have the feeling no. The result should be 983. I always have this end part. I think I don't know how to work my calculator when it comes to. Okay, let me. I know what I did. Okay, let me do it one more time, guys. 15 times 143. One at a time. That's 2,2145. 16 times 91. This is 1456. Then 8 times 77 times 12. This is 7,392. And now I have to add all these things up. And I think that's where I made a mistake. I didn't add them. Okay, that's definitely a different number. So this is 10,993. So divide this now by 1101. That is 10 times. So this is 10 times 1001, which is 1010. Not so hard to calculate. And what is missing is 983. And that is exactly the answer I had found. I checked my answer using Wolfram Alpha. Okay. So there you see a way of calculating even for numbers that are not prime. But the problem is if it's for certain numbers it works. For other numbers, if they have powers of prime in there, if the multiplicity, the way that the power occurs, then it gets more tricky. But at least it's useful. And again, this is a technique that is at the core of the RSA and all the other encryption schemes that we will discuss soon. Okay, so let's go to the last question, the second question. That was number 55. That's about discrete logarithm. This is, again, one of these problems that I said is extremely important for cryptography, because so far we only can solve it in non-polynomial time. In other words, this is one of these famous NP problems. And a lot of protocols that we have, and so we will talk about these protocols, are based on this. And so if NP is not equal to P, we are safe. But if NP is equal to P, then a lot of these cryptographic traffic that we now use is vulnerable. And so the basis is this so-called discrete logarithm. So we have here 2 is a primitive root modulo 19. Now, how do I know this? This was another question, 54. There's only one way to check this, is by listing all the powers of 2 and calculate the modulo 19 and show that you don't get repetition. So you 2 squared, 2 third, to the fourth, not the squaring part. So every single power separately, and that you get the mod 19, that you get all the different numbers. Modulo 19, that every number modulo 19, of course, apart from 0, appears that way. That is a primitive root modulo 19. Now, to find that something is a primitive root modulo 19 is not easy, and there's no golden rule to find it. There's no algorithm to find it other than trying it. So how can we use this in cryptography? That's the beauty of it. So the NSA, for instance, has a list of of moduli, big, huge prime numbers, and primitive roots of these prime numbers. These are public information. And they say, people use this because we know that this is very robust against any known attacks to this discrete logarithm. So there's no secret in knowing what 2 is. So why is it then? So what we know is, so what is the log of the discrete log? So let me write it. I don't like the notation there, so I'm going to just write down the discrete log of 5 to base 2 mod 19. There's quite a lot to say, but what do you do? So solution, and it's a stupid way of doing it. That is why it's so hard to break. You just check every single power. 2 is so, and every time you check, is this the same as 5? This is where you check it with. So you check against 5. Okay. So this is this equal to 5? And this is what we're going to do. So what are we going to do? 2 to the power 1, and of course it's always mod 19. 2 to the power 2, that is 4 mod 19. No, that is not 5. To the power, not squaring, and this is where you might think, no, the next one. Now, what is that? How do you get the next one? By multiplying with 2. So I can multiply this with 2, right? So this is 8. Well, sorry, that's not, no, sorry, I shouldn't say at this point. I'll say it soon. 2 to the power 4 is 16 mod 19. 2 to the power 5 is 32. But 32 is too big, so we have to subtract 19, and we get 13 mod 19. Is that correct? Just to make sure. Yes, okay. And now 2 to the power 6. So from there to there is multiplying with 2. So this is 64, but you can also say it is also 2 times 13. So it's 2 times 32, which is 64, sure, but it's also 2 times 13, which is a smaller number, and I always like smaller numbers. So mod 19, but what is that mod 19? Well, that is the same as 7 mod 19, right? Just subtract 19. So take another, multiply, so not squaring now, but we each time multiply with 2. We're making a geometric progression here. 2 to the 7th, so multiply this with 2, that is 14. That is still not what we want. It's very frustrating, right? That we don't get what we see. We're looking for 5. So this is the question, right? Is this 5? So this is not, of course, it's not 5, right? But is 5 appearing? And so far we haven't seen 5, so we have to keep going. 2 to the 8. We just double this one, that is 28. Mod 19, that is the same as 9 mod 19. So no, we're not there yet. 2 to the 9th, that is 18. That is mod 19. Mod 19, sorry. No. 2 to the 10th, that is 36, right? Mod 19, which is the same as, what is that? 36, 17. Mod 19. Oh, damn, it doesn't, we're not getting 5, people. 2 to the 11th. Now, since 2 is a primitive root, we must at some point get 5. That's exactly what it means to be primitive root. So, to the 11th, that is 34. Like, I'm always doubling this guy, right? 34, which is the same as 15, mod 19. Now, we also should keep a little eye on of whether we have a duplication here, because that should not happen, right? Duplication of these numbers can only happen after you have, because this is a primitive root modulo 19, so all these powers have to be different, okay? Then that's how we can see whether we made a mistake, but that's not the case with 2 to 12. Wow, they really send this on a goose chase here, right? So this is 11 mod 19, 2 to the 13, that is 22, which is the same as 3 mod 19. Okay, no, we're not getting there. 2 to the 14, that's equivalent to 6. Doubling the last number, right? Mod 19. 2 to the 15, that is 12. Mod 19, no, we're not there yet. 2 to the 16, that's equivalent to 24. This is it. So the log is what? This power. So the logarithm of base 2 is 16. So make sure that you read these numbers correctly. what you're looking for is basically the log. Now 2 to the 16th, it's, well, I think this can go still in my compute in 2 to the power 16 is 65,536, and so what I'm saying, that number is equivalent to 5 mod 9. 9, 10, 16, 7, well, okay. Yes, no, yeah, okay. Anyways. Okay, and then I think the question was also the discrete logarithm. I don't know what happened here. Discrete log of 5 to base 2, and the other one is the discrete log of 6. I think that was the other problem. Now we have found 6 here, so we found 6 here, and so that means it's 14. So remember, it's the power here, right? So 14 is the discrete log of 6 modulo 19 with base 2, with respect to base 2, but okay. So yeah, so there are a couple of, the base place and the modulus place, right? So in the definition I should mention everything, but okay. And there is no way to predict this. You see, well, they deliberately, of course, choose things that are kind of far down the road. How many more powers are there? Well, 2 to the 17th and 2 to the power 18th, but 19 is a prime, so we already know that this is equivalent to 1 mod 19. Okay, so this is the only one that we haven't seen, which is 10, right, mod 9. And notice that we have now exactly all the powers. We have 1 here, where is 2? We must have seen 2 somewhere. I don't see 2. Where did 2 go? Oh, of course, 2, because I put 5 there, so 2 is 2. 2, and then 3, and 4, and 5, and 6, and you can see all these numbers that we found here are all different, exactly all the numbers from 1 to 18. Of course, not 0. All right, that's the homework.